Morning, good afternoon, and good evening, everyone, wherever you might be. And today we're going to be talking about derivatives and integrals of vector functions. So last time we talked about um, what vector functions are. So it's basically a vector, and each of its components are functions, right? So last time we talked about we have here some vector r of t, because it's a function, and its components are also functions with respect to t, right? Now we're going to talk about a little bit of application of calculus towards these vector functions. So yeah, let's begin. So later in this chapter, we're going to use vector functions to describe the motion of planets and other objects through space. So we're going to be doing a little bit of astronomy here. Here we prepare the way by developing the calculus of vector functions. So here we're basically going to apply calculus. Let's begin with derivatives. So this is basically Calc 1 stuff, derivatives. So I'll do a little bit of background, but this is basically Calculus 1. So hopefully most of you have already taken Calculus 1, but if not, then that should be fine. I'm going to walk through it as I go. But basically, a derivative is analyzing a rate of change of something. So when we want to find the derivative, we're basically trying to find how fast that object is. So rate is how fast that object is, and how fast is it changing, right? So let's say we have a car, it's going at a certain speed, but obviously it doesn't have a constant speed, right? Because I don't know, there's traffic or it's going to park or those types of stuff. So obviously there is some sort of velocity and acceleration to that. Velocity because there's also direction as to where the car is going. And so that's basically derivatives. So we're analyzing the change of the rate of something, if that makes sense. So we're going to apply that concept here in a vector function. So the derivative, so yeah, so the derivative r prime, right? We use r prime to denote it's a derivative. So the derivative r prime of a vector function r is defined in much the same way as for real valued functions. So here we're going directly into a definition. So yeah, this would have been easier if we've taken Calc 1. So I highly suggest you do Calc 1 first. But if not, then that's all good. So here we're getting the derivative of r with respect to t. This is in Leibniz notation. This is another notation. This is Newton notation. And here another Calc 1, which is getting the limit. So here it's actually the limit definition of a derivative, but we're applying it to vectors. So the limit definition is this, r of r times t plus h minus r of t, or minus that function over h. So there is an explanation as to how this works, but again, this is calculus 1 stuff. And so this is correct, or this is accurate if the limit exists, right? So we're saying the derivative is this limit if the limit exists. So actually, I should have written that. If limit exists, right? But yeah, I mean, if you go through Calculus 1, this is the first thing they teach you, limits, the idea of limits. And then you guys hop into derivatives using the limit definition. And pretty much you're able to find the derivative of any function, not just a vector function, any function, f of x, um, using this limit definition if the limit exists. Um, and then, yeah, once you go through Calculus 1, you'll learn different derivative techniques. So you'll learn like product rule, chain rule, and stuff like that. So yeah, that's a derivative. But yeah, that's all Calculus 1 stuff. So probably review Calculus 1. Okay, so the geometric significance of this definition is shown in a particular figure. So I'm actually going to show the figure. Um, oh, crap. Wait. So I have two figures here, which is funny. I don't know which one to show, so I'm just going to show both of them. But here's how we'll see the significance, at least according to this textbook. So it's these two figures here. I'm gonna see which one it's saying, but the geometric significance. So here we have points P and Q. So they both have P and Q in both figures. P, Q, P, Q. Sure. Um, Basically, these points have position vectors R of t and R of t plus h. So that makes sense, right? Because we have a vector pointing here to P, and we also have another vector here pointing to Q. So R of t is pointing to P, and R of t plus h is pointing to Q. And so therefore, we also have a vector PQ here, right? So a vector PQ. And this represents the vector that is R of t plus h. So I'm going to say this is R of t plus h minus R of t. And this makes sense, right, in vectors? It's basically the difference of these two. If we translate them in terms of R of t. And apparently, this can be regarded as a secant vector. So that's what it was saying. So this is called a secant vector, PQ. Interesting. And if h is greater than 0, the scalar multiple 1 over h, okay, the scalar multiple 1 over h times r of t plus h minus r of t. So it's talking about this thing here, that scalar multiple. Apparently, it has the same direction as r of t plus h minus r of t. So what it's saying is that this has the same direction as this, which we can see that, yeah, based on the graph. So yeah, they have the same direction. And as h approaches 0, it appears that this vector, so this vector, it appears that this vector approaches a vector that lies on the tangent line. So it approaches a vector that lies on the tangent line, so it's actually talking about this thing, this red vector, r prime of t, which is the derivative. And so what does that entail? Well, for that reason, the vector r prime of t is what we call a tangent vector, which makes sense. So again, another calculus 1 concept. So it's this idea of tangent lines to curves. But here we're incorporating some direction and some motion. That's why we call it now a tangent vector. But yeah, again, another review for calculus 1. This idea of tangent lines, of approximating curves using tangent lines. But in this case, we're introduced to this notion of vectors that are tangent to some curve that we're given. So yeah, r prime of t is a tangent vector to the curve defined by r at the point P. So it's tangent at this point P, which makes sense. We can literally see it, right? Um, and this is true provided that the derivative r prime of t exists and the derivative is not zero. Because if it's zero, then r prime of t would just be a horizontal line where the slope is zero, but in this case, it's positive. So yeah, the tangent line to C at P, C is the curve, at P is the point, is defined to be the line through P. So it's the tangent line is the line through P, so it passes through the point P, and it's parallel to the tangent vector r prime of T. So it has to pass through P, and it's parallel to r prime of T. So we can say that, oh, that's a tangent line, or or a tangent vector, or oh, we can say that's a tangent vector or a tangent line. So that's basically the definitions. And so the following, we have here a following theorem, and this gives us a convenient method for computing the derivative of a vector function r. And basically, we just have to differentiate each component of r. So differentiating is, again, another calculus 1 concept. If we have a function, we can differentiate or take the derivative of that function, and boom, we're done, right? And so here in this case, we're just going to do the same thing, but this time when we encounter a vector function, we just differentiate each component, which is also a function. So we basically take the derivative of 3 different functions, and then that's it, right? So here's the idea, which I'm just going to directly write the theorem. Theorem meaning it cannot be disputed because it's a fact. So here, the theorem is that if we're given some vector function r, which has composite functions, f, g, and h, could be any, honestly. I'm just using what the textbook is telling me. Oh, they even translated it to IJK, so I guess I can do that. So we have IJK format here, which is not, oh, I put I. So sure, I mean, we can put it in IJK format because why not? Uh, so that's an IJK format, and f, g, and h are basically differentiable functions. Then the derivative of our vector function is basically the derivative of each composite function. Done. And we can translate that again to IJK format, which I might as well do just to complete the theorem, I guess. So f prime t I plus g prime t j plus h prime t k. So that's the theorem. And we have a proof. I'm not going to go through the proof anymore because it's a limit definition proof. Um, and we even have a unit vector that goes along with the proof. I'm not going to go through it. Okay, let's go to an example. So the first thing we want to do, or at least the textbook is telling us to do, is you want to find the derivative. Obviously, it's going to be finding derivatives of the given vector function. So we have r of t, which is 1 plus t cubed I plus dE to the negative dj, and then plus sine of 2t, so a trig function, and that's k. Oh, my bad. That's k. So here we just apply the theorem, right? So we want to find derivative of each composite function. So here in math, what I like to do is I like to label my steps so I don't forget, because there's usually a pattern here somewhere. So let's take the derivative. So let's say we have 1 plus t cubed, and so the derivative of that is just 3t squared. Now here we actually have some techniques that we might want to use from Calculus 1. So the technique is basically if we're given a number or just some constant number, then that's just going to be a 0. Plus, if we're given this variable with a power, then we want to bring down the power. So we bring down the 3, we have 3t, and then we subtract that power by 1. So we have 3 minus 1, which is 2. And so 0 plus 3t squared is just 3t squared. So again, another calculus 1 stuff. These are different derivative techniques that we just have to memorize. But again, we can use the limit definition. But to be honest, it's better to just use these techniques because it's way quicker. And so we have that. Now we take the derivative of dE to the negative t. So here we actually use a product rule. So another one of those calculus 1 stuff. So we can just do that. So here again, calc 1 stuff. So that's a product rule. So the product rule, let's say, because these are two functions, right? So we have this thing here and this thing here. We multiply those two, that's why it's a product. That's why we use a product rule. At least that's how I would do it, unless you guys know any other ideas. So yeah, basically, if we're given an f and a g function, and to take the derivative of this thing, well, we want to take the derivative of the first function times the second function. We add, and then we multiply the two again, but then we take the derivative of the other function. So that's the formula. And so that's exactly what I'm doing. I'm taking the derivative of the first function multiplied by the second, then I add it. This stays, t, and now I take the derivative of the second function. So what's the derivative of t? Well, again, okay, actually that's different. So another technique here is if we're given just a variable x, we take its derivative. This is just 1. That's it. So it's just 1. So if this is 1 times anything, in this case e to the negative t, well, this just gives us e to the negative t. And then here the other one, okay, we have a t, we multiply that t. And now here we take the derivative of e to the negative t. So e to the negative t is, well, the derivative of e to the t is actually the same thing. So that's one of the what do you call this? Exceptions. And so if we take the derivative of e to the negative t, well, we put the negative up front. Well, actually, we take its derivative, or we copy, and then we multiply it to negative t, and this is another rule that we call chain rule. So we take the derivative of the outside, then we go inside and we take the derivative of the inside function. So that's what we're doing here. So here again, we have two functions. So here, an idea of chain rule. Chain rule is a composite function. Yeah, what I mean by composite is there's a function inside of a function. So this is a high school pre-calculus thing. And so to get this derivative here, well, we have to take the derivative of this first function, right? Okay, correct me if I'm wrong, but we have to take the derivative of that first function. And then we multiply that, or we get the chain rule, so we get the derivative of the second thing. So yeah, a little bit of calculus 1 review, but that's the idea. So we take the derivative of the outer, and then we multiply it to the derivative of the inner function. And so here, in this case, our outer function is e to something, and then our inner function is -1 times something. So that's what we're doing here. And if we equate this, well, we'll get, oh, so here we take negative t. The derivative of that is just, so if we're given a number and we're given a variable, well, the derivative of that is just the number. We take out the variable. So there's going to be -1. E to the negative t. So it's actually just negative e to the negative t. Right? And so as time goes by, you just start to memorize all of these things. Okay, why did I erase that? Well, I meant I'm gonna copy it here. So we have e to the negative t, and I add it to t. So, well, it's actually, I just added to here minus, yeah, and so this is just minus t e negative t. So I'm just cleaning it up. Okay. And funny enough, we can actually factor something here. So when we factor, we're going to factor out e to the negative t. And so this is just 1 minus t, e to the negative t. Which if I check my textbook, yeah, I got it. So again, calculus 1 stuff. Yeah. And lastly, we take the derivative of sine of 2t. So now this is tricky because it's a trig function. But it's actually, again, just chain rule. So it's this idea of an inner function inside this function inside a function inside a function. And if we take the derivative of that, then we just take the derivative of the outer multiplied by the derivative of the inner. And so here, in this, if we apply it here, well, we take the derivative of the outer. So what's the derivative of sine? Well, that's actually just cosine. And personally, it's something I memorize. But you can use the limit definition to do this. I personally didn't because I don't like it too long when we have these techniques that we can just use. So it's cosine. And if you take the derivative of cosine, that's negative sine. And if you take the derivative of negative cosine, that's -1 times. Wait, what am I saying? Take the derivative of cosine, that's negative sine. Take the derivative of that, that's negative cosine. Yeah, if I'm not messing around. And if I take the derivative of that again, then I get negative 1 times negative sine. And I get that's again positive sine. So it's again and again. So like if I take derivative of sine, I get cosine. And if I take derivative of sine, I get negative sine. And if I take derivative of that, I get negative cosine. And if I take derivative of that, I get negative of negative sine, which is again back to sine. So it's this like looping thing. So just a fun fact. So anyways, before I digress, so we take the derivative of the outer thing times the inner function 2t multiplied by the derivative of 2t. And the derivative of 2t, again, we're given a number and a variable. So this is just 2. And so we multiply it by 2, so we get 2 cosine 2t. And that's it. So again, just some calculus 1 stuff. Now, I went too much here, but that's how you find derivatives. And this is pretty much like the bulk of calculus. You just learn how to take derivatives, learn how to take limits, and that's pretty much it. Anyways, so now we got the derivative of each composite function in our vector function. And now we can, now we can just get our derivative here. So the derivative of our vector function is just, we'll write it in ijk, because why not? Which is 3t squared I. We add that to 1 minus, okay, that looks like a vector. That's funny. 1 minus t e to the negative t. This is j. And I add it again to 2 cosine of 2t k. And that's it. Yeah, so far so good. Or I can even translate it to, okay, I'm going to be honest, I prefer it in vector form. So I'm going to do that real quick. So I'm going to say this is 3t squared, 1 minus t e to the negative t, 2 cosine 2t. And so that's the derivative of our given vector function. Okay, let me box it properly. And we're done with that. Now moving on to B. So that was A. Here we find the unit tangent vector. At the point where t is equal to 0. So what do we mean again when we say unit tangent vector? Well, I actually forgot to define this, so I should have done this before this example. So let me quickly define what a unit tangent vector is. Because we know what a unit vector is, not a unit tangent vector. So a unit vector is a vector of length 1, hence the word unit. But what's a unit tangent vector? Well, here I'm just gonna write exactly what the textbook says. But a unit is a unit tangent. Oh, a unit vector. Okay, so a unit vector has the same direction. So, okay, cool. As what? As the tangent vector. So if the tangent vector is going at a certain direction or slope, then that unit vector is also going in that same direction. So here we're saying a unit vector that has the same direction as the tangent vector is called oh, there we go, the unit tangent vector. Which we'll just assign as t. So we call that the capital T, unit tangent vector, and is defined. So here's how it's defined. Okay, I need to move this more. I want to give space. Okay, cool. So the way this is defined, a little bit more, not too much, maybe here. It's defined as some unit tangent vector. So there's a function and it's given by, oh, look at that, the derivative of our vector function divided by its length or magnitude. So it's actually pretty similar to a unit vector. The only difference is we take the derivative. That's it. But it's the same thing. And so this has, again, a length of 1. But we just take its derivative for it to be a unit tangent vector. That's it. But it's the same as, or was it? I'm actually going to look at it real quick. I think it was 12.2 if I'm not mistaken, with vectors. There we go. So we have a unit vector. A is a vector that has components, I don't know. A has, let's say, x, y, z divided by its length. But here, we just take its derivative, and then that's now what we call a unit tangent vector. So that's the only difference. So this is actually still equal to 1. I hope. I think it is. Yeah, should be, because it's a unit. So that's the next thing we're going to do. So we want to find the unit tangent vector at the point where t is equal to 0. So at the point where t is equal to 0, well, here we're given our r prime of t. So we just have to plug in t equals 0. Right? That's all we have to do. So if we were to use our formula, so we want to find the unit tangent vector when t is 0, and that's basically our derivative of the vector function when t is 0 divided by its length, and we get a number out of that. So r prime of 0, well, okay, let me see. What do we get here? Let me see. Okay, so if we make this 0, well, okay, let's take it step by step. I'm not I'm not that good. So we have r prime of 0. So this is 3 times 0 squared, so that's 0, comma. This is 1 minus 0, e to the negative 0, so that's e to the 0, comma, 2 cosine 2 times 0. And this is just 0, 1. And this is cosine of 0. What was that again? I totally did not understand my... Okay, so this is 1. And then this is just 2. And now what's the length? Well, the length of this thing is just the length of this unit vector. Or this vector, I mean. Just a regular vector. So we get 0 squared. So here we're just using distance formula. Here we're supposed to get a number. So we have 1 plus 4, so square root of 5. And yeah, we're done, hopefully. So here we basically have 1 over square root of 5 times this vector. And so we got vectors. We got 0, 1 over square root of 5, 2 over square root of 5, and we're done. This is our vector. And I hope I'm right. Yeah, they did it in IJK format, so that's pretty cool. We can make it in IJK format, but it doesn't matter. Okay, let's do example 2. I hope that made sense. Maybe not the derivative part, because I didn't talk about derivatives. I did take a Calculus 1 course last year. I will do a bit of review on that maybe, if I have the time. At least for those who haven't taken calculus at all. 'Cause, yeah, I mean, this is calculus 3, so maybe I should have made videos on calculus 1 and 2, but didn't really think about doing that before. I just tried doing this now. So yeah, I will make videos. Okay. So example 2. Here we're given a curve. So for the curve, r of t, so here we're given yet another vector function. Square root of ti, so this is again an ijk format, plus 2 minus tj, and here we don't have a k. But we do know that in in vector functions, or was it in vector functions? I forgot. Anyways, let's scrap what I said. So here, we want to find r prime of t. So we want to find the derivative of our vector function. And we also want to sketch the position of, what's this? Vector r of 1. So here we just plug in, and it's tangent vector. So tangent vector just means its derivative at that point, or at that vector, I mean. So we have r prime. So here we're actually starting to dive deep into what really are derivatives and how they apply in terms of vectors. So let's do that. So the first thing we want to do is find r prime of t. Or again, if we take our previous step, then we want to find derivative of each composite function. So I'm just going to do that. So again, r prime of t. So I'm going to write it in vector form. So this is going to be square root t. Then we have 2 minus t. Right? And so our r prime, or our derivative, is just going to be, well, this is t to the 1/2. And so I can use my derivative techniques here. I can, again, bring this down, right? My exponent, 1/2 t, 1/2 minus 1. And so I get negative 1/2. Then I do 1/2. And then here I bring it down 1/2. Then I get 1 over 2 square root t. So this is 1 over 2 square root t, comma, and then 2 minus t, the derivative of that is, so again, if we're given a constant, that's 0. If we're given a negative t, well, that's just negative 1. So it's just negative 1. So that's it. So we can translate this to ijk, but I don't really care about it. So here we found r prime of t, and here we want to sketch the position vector r of 1 and tangent vector r prime of 1. And so how would that look like? Well, so the first thing we want to probably do is we want to find r of 1 and r prime of 1, right? Before sketching, we want to find what it is we're actually sketching. So r of 1 and its derivative. So here we just plug in what we know. So r of 1 is just, well, we plug in t equals 1. So we have square root of 1, which is 1, 2 minus 1, which is 1. So that's the vector 1, 1. And another thing we know is r prime of 1. So this is 1 over 2 square root of 1. So that's basically 1/2. 1/2 minus 1. So how do we sketch this thing? And it's a position vector. So what does that mean? It starts at the origin. That's the tail. Sketch r of 1 and r prime of 1. And apparently this is 2D. Do I know? I only have two composite functions. Or two components. Not even functions, two components. So I have my xy plane. So r of 1, well, we can actually translate this to slope. So this is that change in x comma change in y. And so our slope is change in y over change in x. So we can do that. So it's 1 over 1, so it's just 1. So there's actually just the y equals x. Y equals x. I'm not sure if that's how it looks like though. But yeah. And so from the origin here, we were going to this point. This is 1, 1. And this is my r of 1. So r of 1. Should have done red, but it's okay. R of 1. Now my r prime of 1, I put in purple. So this is again another change in y over change in x. So we have -1 divided by 1/2. We can just multiply -1 times 2 over 1. We get -2. So this is going probably this way, but a bit steeper. So maybe um, um, okay, I'm looking at the solution here, and my slope is right, but it's being drawn. The tail is starting from 1, 1. Why is that? Um, so we draw the position vector r of 1, which we already did. It starts at the origin, and then its tangent vector starts at the corresponding point 1, 1. So this doesn't start at 0, it starts at 1, 1. Yeah. So let's see that. Oh, so basically what it's saying is if this is r of 1, then r prime of 1 is something steeper that goes like that. This is r prime of 1. And well, we can actually, I don't know why they drew a curve here, which is funny. The curve is a plane curve and elimination of the parameter from the equations x equals. Okay, we have parametric equations, yeah. Uh, that's interesting. Hmm. Okay, so that's, yeah. So apparently what the textbook is trying to say is that this thing here, oh, my bad. I'm trying to draw it nicely. But this thing here is a curve. And this is a tangent line to its curve. This is a plane curve, which makes sense. Yeah, that's interesting. Okay, next we go to example 3. So here is where it gets a bit interesting. So example 3, we are being asked to find parametric equations. So we'll do that obviously. So we're being asked to find parametric equations for the tangent line. So here we want to look at derivatives because we're looking at tangent line. For the tangent line, the helix. So here we're already given a helix with parametric equations. And so these parametric equations of the helix are the one that kind of spirals like that. That's a helix. It has these parametric equations. So x is 2 cosine t, y is sine t. Oops, my bad. Y is sine t, and z, right? Z is z. So this is a helix. The movement of some particle here is a helix. It's gonna spin around and around. Okay. Now, how can we do that? How do we find the parametric equations? Well, for one, we can actually translate this into a vector equation, right? And then we can take the derivative, or honestly, we just take the derivative of each of these parametric equations. We don't need to make it hard on ourselves. Oh, okay, I missed something. So we want to find parametric equations for the tangent line to the helix with these parametric equations at the point. Oops, missed it. At the point 0, 1, and pi half. And so the way we can do this is we can just take the derivative of each parametric equation, right? And then once we do that, we just well, we basically find the t to which this point occurred, the 0, 1, and pi half. And once we find that t, we just plug it in our derivative vector function. And so we can get that corresponding. I mean, do we need to do that? Maybe we can. Uh, Trying to think. But yeah, I mean, it's just, I'm trying to think. Hmm. Okay. Um, hmm. Helix invention. Okay, let's think about it. Well, I mean, I kind of looked at the key, but whatever. So here we want to, okay, maybe the first thing we can do is find the when or at what t did we get to this point here, 0, 1 pi half? What t did we get to there, right? So here we can just say find t value, or value of t. Oh, look at that. Z is equal to t is equal to pi half. Can we try? Okay, let's do 2 cosine pi half. This will give me 0, right? Because cosine pi half is 0. Should be, yeah. So this works. Okay, let's try something else. Maybe sine of pi half. Well, sine of pi half is 1. So again, this works for the y. And so t is pi half. So we were able to get that. So when it reaches point 0, 1 pi half. So that's t equals pi. Now the next thing we want to do is find parametric equations. Or do we find parametric equations? Um, Actually, not even find parametric equations yet. We want to take the derivative, right? So we want to find derivative of each parametric equation. So here we were given that x is 2 cosine t, so its derivative is just going to be 2 negative sine. So it's just negative 2 sine of t. Chain rule t, we just got times 1, so that's just that. And then y prime, so we get the derivative of our y, so that's just cosine t. And again, we get the derivative of our other parametric equation, that's 1. And then we can plug it in. So here we basically find tangent vector, right? Not yet parametric equations. Here we're just trying to find a tangent vector, which is actually similar to what we did here. We have this vector, and finding its derivative, which, if I'm not mistaken, will give me a tangent vector, right? So kind of like this. Gives me a tangent vector at that point. So we're trying to find a tangent vector at t value, at given t value. So at given t value. So we actually computed our t, which was pi over 2. So we can say, okay, so we get pi over 2 here. R prime of pi over 2. And so, actually, I should have. So when we found this derivative, I could have just plugged it in, right? So this is r prime of t. And so this is a derivative of the vector function. So here we just plug everything in. And then we do that. So now we find tangent vector. At t equals pi half. So here we plug in pi half to t. And this will give me, let's just complete it. Negative 2 sine pi half, cosine pi half, 1. And this will just give me negative 2, 0. Okay, so we found a tangent vector, and it intersects this point, negative 2, 0, 1. But again, the tangent line is the line that passes through 0, 1, pi half. It should pass that point. So it should pass this point. We've now found parametric equations. Or we kind of did here. See, we parameterized our x and y. Z is just a constant. But yeah, so we want to find parametric equations for the tangent line. And it has this initial point here, these initial points. And so we just need to find some sort of t to parameterize that. So what is that? So the tangent line passes through 0, 1, and pi half. Right? So it passes through that point. And the tangent line is also parallel. I'm actually going to write this out because I'm also a bit confused. So here we want to now find parametric equations. But I'm going to write out what the textbook is saying. So what the textbook is saying is that the tangent line, so we're not even talking about vectors, we're talking about lines. So the tangent line through 0, 1 pi half, passing through that point. And it's also parallel. Ooh, that one's far. Parallel to a vector that has this point. Has parametric equations. So here, the idea is we want to find, again, when we're looking at parametric equations, similar to a line, we want an initial point and we want a direction vector. So our initial point here is this guy over here. And our vector is this guy over here. So that's what makes this weird, right? Because we not only have to find the derivative and parameterize that vector, because I thought it was this one, and we just plug in whatever pi half, and then that's it. But we're trying to find parametric equations here. And so if we need parametric equations, again, we want a point, an initial point, and we also want a direction vector at that point, which we got here, which is this thing. And then after finding that, well, it's just plain old parametric equation. So we have x, which is 0 minus 2t, right? Because we just multiply the t to each of the components here. That's our parameter. Then we have y equals 0 plus 1t. Then we have, oh no, not even 1t. I'm wrong because this is 0. So it's actually just 1. Yeah, so yeah, 1 plus 0t. So it's just 1. And then z is pi half plus t. So we can just say that's negative 2t. And we're done. Yeah, a little bit confusing also for me, because I'm also new to this. But yeah, I'm getting it a little bit. And here we have a graph to show the helix, the path of the helix, as well as the tangent line. And they're both parameterized, so yeah. So it's this thing. Okay. Well, that's that. Just as for real valued functions, the second derivative of a vector function r is the derivative of r prime, right? So now we're going to look at second derivatives. And so the second derivative of the function in example 3, okay, yeah, we have some stuff here. I'm not gonna say that anymore, but basically to get the second derivative is to get the derivative of the derivative. So in this case, here we got this thing. We got this thing. Then the second derivative, which we call r double prime. Basically, we just have to get the derivative of this again, the derivative of this again, and the derivative of this again. So that's that. Okay, fine. I'll write it down for the just a reminder. So here we're saying the second derivative of here, let's say a vector function, and let's denote it as r, is the derivative. Oops, I don't know why that did. Of r prime. So we take the derivative, then we do it again. So it's basically just r double prime is equal to r prime, and we take that derivative again. And so, for instance, we had r prime, which was, what was it? Negative 2 sine t cosine t cosine t 1, right? And so the second derivative would be negative 2. We take this, so negative 2 derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of 1, or derivative of any constant, is actually just a 0. So we get the derivative of 100, that's 0. So yeah, little fun fact there. And we can get the third derivative and the fourth derivative. So we can get r triple prime. R triple prime. We can get r, we don't use prime anymore. We use this notation, r to the fourth. So we get the derivative 4 times. So yeah. And if we get the derivative of 0, it's just 0. Okay, I shouldn't draw the line there. Okay. Now we look at differentiation rules. So maybe we can get into derivatives a little more. Okay, let's see this. So here we have theorems. No, not theorem. We have a theorem, and we have differentiation formulas for real valued functions and their counterparts for vector valued functions. So I'm actually just gonna copy paste this. I don't wanna. Mm, actually, you know what? Uh, it's fine. I'm gonna write it out. So we have a theorem. Yeah, I feel like when I write it, I'll remember it better. I don't know. I just have a feeling. So here, suppose U and V are differentiable. So when we say differentiable, we can take its derivative, no problem. And usually that works when a function is continuous. Usually. Continuous meaning there's no like loops and stuff like that. So this is differentiable. This is not differentiable. We can do it piecewise. We can get the derivative of one of them, right? Okay, so they are differentiable functions, and we say that C is a scalar. So C is a number that we multiply to a vector. That's basically what scalar is. And we've talked about it in like what, 2 weeks ago? 2 to 3 weeks ago. F is a real valued function. Um, okay. So we're actually using four things here. So when we say f is a real valued function, it's a regular function. We plug something in, we get something out of it. Maybe f of x is x squared. So we plug in a 2, we get a 4. We plug in a 5, we get 25. So it's for real numbers. But u and v, so u of something, right? Let's say u of t is a vector that can be differentiated, and it has components that are also functions. And these functions are real valued functions. So f of t could be t squared, g of t could be 2 minus t, h of t could be h of t could be t cubed, something like that. I don't know. Okay, so let's just hop right into it. So one, the derivative. So again, this is another notation for writing derivatives. Um, Derivative, that's what this means. That's what this thing means. Derivative of, oh shoot, I wrote in blue, of u of t, right? So it's a vector function plus v of t is just, well, we just get their derivatives each. So the derivative of the first vector function plus the derivative of the second vector function. That's it. Similar to Calc 1, Calculus 1. So when we get the derivative of two vectors or two functions or two vector functions, well, we just get their derivatives normally. Okay, another one, d dt. So again, the derivative of c is again a scalar, times u of t. So we multiply this number to the vector function. Well, again, it's just similar to calculus 1. We ignore the scalar, we ignore that, and we just take the derivative again of the vector function. Number 3. This one, d dt. So here, there's a new one because we're given a real valued function. So this one's not a vector. And we multiply that function, that real valued function, by a vector function u. What is that now? Well, it's a product rule. So f prime of t, u of t plus f of t, u prime of t. So it's actually a product rule. So interesting. It's a product rule. Now, this is where it gets really new. I was expecting this to be new, but I guess it's pretty similar. Because f of t produces a number at the end of the day. So I guess it should be fine. Um, yeah. Okay, let's see. This one is new. So here we're getting the derivative, and we're using some calculus 3 of the dot product of two vectors. So what is that? So this one's new. But it's actually a bit similar to product rule, where we multiply uh, or we get the dot product of both vectors, but we take the derivative of the first vector function. So it's actually funny. It's similar to a product rule, but here we're just using dot product, right? It's similar to this, but here we're using dot product instead of multiplying. And we know from our previous lessons here in Calc 3, dot product is definitely different from a product rule. Okay, number 5. Here, now we look at a cross product. So there's a little bit, no, this is new for me. Oh, so it is the same thing. It's a product rule, but instead of multiplying or getting the dot product, we're getting a cross product. So it's actually similar to a product rule, but instead of multiplying, we're actually just getting their dot product and cross product. Number 6. And the last one is we're given the derivative with respect to t of u of f of t. So here we're multiplying. Oh, so this we have a composite function because we have a function inside of a function, right? So here we have f of t inside a vector function, which is interesting. So what is that? Well, okay, now this one's tricky. Well, this is chain rule actually. So we get, well, we get the derivative of the outer function, and we multiply that to the inner function, and we get the derivative of that inner function. So again, it's just chain rule. I'm writing it exactly how the textbook's writing. No, I'm kidding. The textbook wrote this one first, then this, but it doesn't really matter because we're just multiplying them. So yeah, that that whole theorem there of differentiation rules. So we can actually prove these. I'm not gonna do that. Yeah, there's a bunch of proofs with summations and stuff. Okay, so uh, those are some interesting stuff. Yeah, yeah, very interesting stuff. It's too advanced though, so I'm not gonna do it. Okay. Uh, Theorem 4, what was that saying? If RFT is, I'm gonna double check something. If the length is some constant, then its derivative is orthogonal to RFT for all t, which is fascinating. Um, yeah, it's fascinating to look at this. Um, oh, okay, okay. Theorem 4. If a curve lies on a sphere with center the origin, okay, then the tangent is always perpendicular to its position vector. So it's just analyzing movements here. It's analyzing motion. I'm gonna turn on my lights, dude. I can't see anything. Okay. Um. Oh, now it's too bright. There we go. Okay. Let's move on to some integrals here. So here is calculus 2. Okay. Hmm. So here we're actually going to only use a definite integral. We're not going to do any indefinite integrals. Again, this is for calculus 2. If you haven't taken it, I'm really sorry. But I might do some videos on reviewing these stuff. Yeah, I've taken this last quarter. Um, yeah. And then calculus 1, I've taken it 2 quarters. So calculus 1, I've taken it in the winter, and then this one I've taken it in the spring. Um, I'll try my best. Let's see how we go. maybe to start, um, for derivatives for Calc 1, let's say we have a car. We have a car, right? And um, as it's moving, well, it's moving at some speed, right? So let's say, okay, now we're not talking about integrals, we're talking about derivatives. Let's say we have a 2D plane. Um, we have time and we have velocity or speed, doesn't matter. And our car is going like that. Or you know what? Screw it, like this, straight. So what does this say? Well, its velocity is constant. And so it's going constantly at this speed. Let's say it's going at 28. Let's say this is uh feet per second, question mark, and this is seconds for time. So the car is going at 28 feet per second consistently, right? So the way derivatives work in a nutshell is given some time, let's say after 5 seconds, what's the speed? Well, it's 28. After 10 seconds, what's the speed? Well, it's still 28 because, okay, I meant for this to be constant because this is constant, still 28. Now, another way we could have done this is pretty easy. If we have a distance and we divide it by time, then we get its speed and velocity, speed or velocity. But what if our speed in real life situations, it accelerates? Now that's not constant, right? It's going up and down. Well, here, what if I say, okay, after 5 seconds, what in the world is that speed? Well, here we can see it's below 28, but what exactly is it? Well, we use this thing called derivatives, and that's how we can find it. Now, if we go to more basic things before going into that, well, we can actually find a function, maybe a parabola, maybe a parabola, maybe a parabola. And let's say, oh, the car here kind of accelerates, right? The speed is increasing. And then when it reaches, oh, my bad. When it reaches this peak, okay, I should stop doing that. When it reaches this peak, well, it's slowing down here, and then here it kind of stopped, right? It's slowing down. Here it kind of stopped. It was actually like slowing down, slowing down, slowing down. We put a bunch of tangent lines. Tangent means it touches the curve or it approximates the curve. So these are a bunch of tangent lines. Those are the purpose of derivatives. It's kind of like taking a screenshot of a car at a certain point in time. But what's the speed of that, right? So how does that rate or how does that speed change over time? I hope that makes sense. But now when we talk about integrals, well, here we're given the distance. So basically, that's what derivatives are. It's analyzing how fast this thing changes, how the rate changes. That's it. And for integrals, well, it's basically the reverse. Here we're given a distance and a time. Here's the distance that this car covered. That's the distance. And so how do we get the speed of a car at a given Actually, I think I'm wrong here. Wait, let me double check. I feel like I'm wrong. Um, hmm, yeah, I was wrong. For my bad. So for derivatives, we're given a distance. Now we want to find the speed. Distance. Actually, maybe distance. That's the distance covered by the car. And so we want to find the speed at a given point in time. That's it. My explanation was right, but I put velocity here, which was wrong. It's supposed to be distance. Now, for my integrals, here now I'm given my velocity. And now I want to find what's the distance. So it's basically the reverse. So again, I'm given a velocity. Maybe it goes here. Now I want to find what's the distance that I covered after a number of seconds. So let's say after 5 seconds. Well, that's actually just the area under this curve. And how do we get the area under that curve? Well, we use this thing called calculus. We use integrals to do that. So basically, integrals is the opposite of derivatives. And so we're going to look at that now before yeah, eternally. Okay, so the definite integral of a continuous vector function r of t can be defined in much the same way as for real valued functions, except that the integral is a vector. Okay. So here now we're getting the integrals of vectors instead of functions. So if previously, okay, let's see this. If we have a function and we get its derivative, and let's say that gives us, I don't know, that gives us a different function, g. Now, if we get the integral, so that's an integral. It's like a weird looking s. We get the integral of that function, and we just put dx there because of x, and then dx here. And then we just put d. Well, this actually gives us f of x, which is this one. That's how they're inverses of each other. So we take the derivative, and then we get its integral. Well, we'll get this back, right? So that's that. Now for definite integrals here, well, here is so hard when we haven't taken calculus too. Okay, so my tip is please review calculus 2, maybe, in order for this to make sense. I'm just gonna hop right into it. Okay, so we do an integral for a vector. So here we can express the integral of r in terms of the integrals of its component functions. So again, it's actually the same as the previous one, but basically, if we're given a vector, we're given some vector function here, right? Well, if we get the integral of one of them, then we're just getting the integral of all of them. That's it. And h of t. Okay, but the textbook makes it complicated, but sure, we can use that. I mean, it's another way of writing the integral. So yeah. So basically, if we have a definite integral, so here we have bounds for a definite integral. So we get the integral of our vector function. And this is the same as getting the limit of Riemann sums. So again, another calculus 2 fact is, well, the limit of Riemann sums is we have a curve and we divide it into rectangles. and we keep on dividing that until the rectangles are really, really, really small and we reach infinity, well, then that's the integral. So we'll basically get super, super, super close until we get the exact area of the curve. That's what's fascinating is that integrals and derivatives all come from limits. That's why the first thing that or I think in my experience, the first thing that I learned in calculus was this idea of limits. So, okay, here we're just using a summation. And then here we're using a sampling t. So again, another calculus 2 concept. And then here we're using that change in t. So another calculus 2 concept. And we're saying that this, well, is equal to, again, the limit of Riemann sums of all of our components. So it's just basically the limit of Riemann sums. I'm getting flashbacks of these things here. F, E, I, or sub I, delta t. This is I. Okay, I'm gonna put this back because it's a little bit long. So the notation of Riemann sums, we add this to literally the same thing, but a summation again. Ti delta t. This is j. Let me do another one. Keep doing I, right? Yeah, I keep doing I. H. So when we say sampling, well, how do I explain this? Okay, I'm gonna explain it a bit. So basically, if you want to get the area under a curve, right? So you want to get this area. We can divide it into rectangles, right? Then each rectangle has, let's say this is T, right? Let's say this is T. Each rectangle has, this is T, oh goodness me. This is T1, this is some Tn. T1, T2, T3, T4, all the way to Tn, right? We have a couple of points here. So we have T1, T2, T3, T4, T5, okay, T6. Sure, T6. Where's my pen? T6. And if we get the sum of all of these rectangles, basically that's what this means. If we get the sum, if we add up all the area of a rectangle, which is just length times width, well, we should get as close to the actual area of the curve. And if we get its limit, meaning if we make the rectangles very, 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 very small, then we reach the some n that we don't know, to a million, to a billion rectangles, to infinity here. Well, we're gonna get the exact area of the curve. And ti, this notation is just like some ti here. So some ti is, I guess, t1, right? This is a ti. So all of them are just ti. We're basically adding all of them. So that's the idea. And then what's this delta t? Well, it's the change in t. So if we have a rectangle, right? This here is that. And then this here is the function. So r of ti. And so if we multiply the length, so the length times its width, well, we get an area of this thing. And we keep doing that. So that's why we do a summation. And then we get the limit of that to infinity. Then we get exactly the integral which Newton created, apparently, which is a more convenient way. But here, yeah, we're just using the limit of Riemann sums, which is basically the integral. That's really all it is. And so we have the integral of our vector function, which is again just the integral of each of its component functions. So it's, I think it was f dt, right? We say that's I, we add it to what was this, g dt, j. Okay, maybe put this a bit back. So the thing with integrals is it's really, really a hell of a computation. So let's just keep going. H of t dt. Okay. So yeah, that's the idea here. So if we want to get the derivative of a vector function, we get the derivative of each of its component functions. And if we want to get the integral of a vector function, then we want to get the integral of each component function. So it's the same idea of doing one for this, then doing all of it for that. Okay. Ooh, so we actually have a little bit of calculus here. But yeah, so this means we can evaluate an integral of a vector function by integrating each component function. So we can extend the fundamental theorem of calculus. So what is the fundamental theorem of calculus? So I haven't covered that, but basically what it is so FTC, fundamental theorem of calculus, is the idea that derivative are inverses is inverse of integral. So they go hand in hand. That's just, yeah, that's it. So that's the fundamental or the basic theorem of calculus. So when you get the derivative and then you get its integral, you'll get back. So here's the idea. So we can actually extend the fundamental theorem of calculus to continuous vector functions. So when we say a function is continuous, we can differentiate it, or we can take its derivative, and we can integrate it. We can integrate it. We can get its integral. So I'm just gonna write that. So a fundamental theorem of calculus in vector functions. So this is just the extra idea here is this idea of vectors. But really, fundamental theorem of calculus starts with functions in its core. But yeah, in vector functions are this. When we get the integral, or the definite integral, of our vector function, right, r of t, well, this is equal to capital R of t. So here we just integrated a, b. Here, r of t is the antiderivative. Okay, I'm using a new term. Okay, when we get the derivative of this r of t, it's actually just r of t. And when we integrate r of t, we get r prime of t. No, we get r of t. Yeah. So when we take the derivative of this thing, we get this thing. That's basically it. We're just using capital here just to distinguish what it is. And then, so here, when we're evaluating integrals, when we have a definite integral, when we say definite, we're defining, there's a defined boundary, which is the integral goes from A to B. How does that look like? Well, okay, a simple example, we'll say r of t, right? Let's say r of t is a function. Let's just say r of t is a function. R of t has this curve here, like that. I go down, I don't know, here, here. Let's say this is A, this is B. Well, if we do that, well, we're getting this specific area. So we're making bounds, and this is a number. This will give us a number. I don't know what number it is, but it will give us a number. So what I'm saying is that if we get the integral of some function, this will be a number, right? That's what I'm saying. Okay, and how do we evaluate it? Well, we do this notation here. So we get the antiderivative, or we call it an antiderivative. So when we get the derivative of a function, we call it the derivative. When we integrate it, we call it the antiderivative. So it's like a pro and an anti, but yeah. So we get the antiderivative, and here we just evaluate it from R, we plug in B. B is a number, A is a number. Minus, we plug in A. And that's it. This will give us some number. Right? That's the idea. It'll give us the area under the curve. So yeah. Okay, it's said in the text box. So I'm just gonna write it. So here, for better explanations, where R is an antiderivative of R. That is R prime. So if we take the derivative of the big R, well, we'll get the little r. And so we use that notation, the elongated s, the long s, for indefinite integrals or antiderivatives. Oh yeah, I'll also mention it. So we use this particular notation, which is this, the elongated s, without a and b. So we don't have numbers. Those are numbers. We don't have numbers there. dt. When we don't have numbers, this is what we call indefinite integrals because we don't define anything. This is just a function. This will give us a function. This won't give us a number. So indefinite integrals, and this is what we call antiderivatives. So a calculus 2 technique that I learned usually is it's easier to get the antiderivative of something and then put in the bounds once we get this R of t. So usually what I would do is get the antiderivative, then I get R of t, and then I put my bounds in there. I put a and b, and then I solve for it. That's usually what I do. But some they like to put the bounds. But yeah, I prefer to get the antiderivative first because I know how to get derivatives. So I just get back the antiderivative, and then that'll give me a function, and then I plug in my bounds, b and a, if there are. If there aren't, then that's it. I'm done. Okay, last example before I yap too much about calculus 1 and 2. So here we're given that if our vector function is 2 cosine t I plus sine t j plus 2t k, so it's an ijk format, then we get the integral of that. So we get the integral of our, or the antiderivative of our vector function, which is just, well, we get the integral of each function here. dt plus, okay, this is long. So something about my experience with calculus 2 is that solving these things are longer than getting derivatives. I'm gonna be honest, this is really long. If there's one thing I don't like about calculus, it's probably integral calculus. There's too much computation. It's computation heavy. So yes, yeah, now let's just get the antiderivative. So here we get 2, right? We leave the 2 alone. Cosine, if we remembered, to get the derivative of sine, it's cosine. So the antiderivative of cosine is sine. So yeah, just bringing something from Calc 1. I put I add, okay, so the antiderivative or the integral of sine, well, it's just negative cosine, right? Because if we get the derivative of cosine, it's negative sine. And so you multiply negative to do that. So it's minus cosine. Okay, I'm not gonna say too much. And I'm gonna add it to 2. And then this is t squared over 2, so it's just t squared. The way to check this is to get the derivative. That's usually the way to do it. And we're done. That's it. What else do we do? Oh yeah, we had a constant c. Because again, a calculus 2 lesson, we always put a constant to show that getting an antiderivative is general, especially for indefinite integrals. So we want to make it as general as we can, because if we get the derivative of this, well, c is just going to be a 0. C will just turn into a 0. So we also want to consider that fact, that we can have constants. So here we say, so C in the context of calculus 3 is a vector constant of integration. So it's the same thing, but yeah, we just have this additional C. Now, what I'm really curious is, where do we put the C if we were to put this in vector form? That's that's what I'm curious about. I don't know where that will happen. Anyways, and what do we also have? Oh, did we? Okay, so here now we're solving for a definite integral. So we have bounds. These are numbers. So we have r of t dt. This is equal to, okay, we have 2 sine t I, yeah, we're just copying this, minus, I say minus cosine t j plus t squared k. I'm putting it all in 0 to pi half. So again, another calculus 2 thing. Yeah, now we just plug in everything. So we plug in the pi half, and then we subtract that to everything 0. So that's why computation's long. But the answer is going to be, so if I plug in a 0 here, I'll get zeros, right? Sine of 0 is 0. Cosine of 0 is 1. Okay, I'm going to do the long way. So I'm going to plug in the pi half. I minus cosine pi half. I'm kidding, j plus pi half squared k minus, and then we do that whole thing again. 2 sine 0 I minus, okay, I'm going to put in the next spot. So that's how computing integrals is really long, because we want to make sure that we got everything. 0 squared, okay. Now I can just compute this normally without doing all of that stuff. And this will give me sine of pi over half. Okay, let me do it. This is 2i minus cosine pi half, which is 0, so that's 0, plus pi squared. Hope I'm right. Pi squared over 4k minus this one. Sine of 0 is 0, so that's all 0. Cosine, so minus, what is this? Minus -1 or negative j. That's it. Yeah. So just to rewrite, that's 2i plus j, because double negative, plus pi squared over 4k. And that's the antiderivative of our vector function. So yeah, pretty long computation for integrals. I mean, back then when I did this course on integrals, last quarter, I yeah. Uh, long story short, good luck. Okay, I'm kidding. But yeah, that's it for this video. We really just applied the calculus 1 and calculus 2 concepts of derivatives and integrals into vector functions, which we're now studying, and we're seeing how both of them work in this context. And yeah, I'm really hoping to see more of these though, like how we can maybe use vector functions to analyze motion, maybe analyzing rate of change through vector functions. I don't know, like a lot of possibilities. And for integrals, it's basically the reverse. Or there could be more applications. I don't know. But yeah, that's it for this video. I'm gonna be doing exercises maybe tomorrow or today. I don't know, depends. But yeah, I hope you guys learned a lot. But yeah, these are confusing if so the disclaimer is I should have put a disclaimer. Um, there should be some calculus 1 and 2 background here. So we have to know really well what are derivatives and integrals before diving into these stuff. So yeah, hope you guys enjoyed, and I'll see you guys in the next one.